Okay, so at the beginning of today's lecture, we would like to prove theorem 5.7.1. The statement of the theorem is a little bit different. I can't say a little bit. It's different from the statement given in the textbook because it is a generalized version. Okay, so the function, the data processing function g of x, here we assume to be a well-behaved piecewise strictly monotone, could be increasing or decreasing real value and differentiable function on the real line. Okay, so that means that we can find piece by piece that at each piece the function g is strictly monotone and differentiable. Okay, and so as we know that g of x will be a random variable again, and we call this new random variable this data processed result y. All right, is a random variable, and this random variable is also absolutely continuous, and we can find a PDF for y, and this PDF is here. So it's a sum. Okay, like a sum of the PDF in, and because there are so many pieces, and so sum over all the piece such that the I sub j is actually, I'm sorry, I forgot to put j here. I sub j. And a I sub j plus 1. Okay? Yep. Okay, so because g may be many to 1, so a particular y may have quite a few different x, such that g of x will equal to y. Okay, so and for those pieces, we will index by I sub j. Okay. All right. So you may have the precise understanding of the statement through the proof. All right. So I will proceed the proof right now. Okay. So first of all, we fix a y in R, okay, and we let I sub j be indices, okay, such that y is in g of ai sub j and ai sub j plus 1. Okay, so for example, in our we raised an we took an example about the quadratic function, right? So all right, so suppose that so g of x is x squared, for example, and if we have a y here. If we have y here, okay, if we have y here, now we can think about that this data processing function g is actually even though itself is differentiable, right, over the whole real line, okay, but but it is not monotonely increasing or monotone decreasing, right? Because but we can decompose it into two pieces, right? So one piece is here, the other is here. Okay. All right. So so you can say that here minus to 0, and this is 0 to infinity. Okay. And you can see that g of x is monotone. It is strictly monotone, decreasing, right? And differentiable. And the differentiable on minus infinity to 0 on this piece. And but g of x is strictly monotone increasing, and differentiable on 0 to infinity on another piece. Okay? On another piece. All right, so for this square function, you can regard that it has two pieces. Okay, it has two pieces, and for each piece, it is strictly monotone. Okay, either increasing or decreasing, and differentiable. Okay, and differentiable. Okay, and for this y, there are two pieces, right? So you can see when we go down here. Okay, so go down here, and so that actually there are two pieces, j equal to 1 and j equal to 2, right? So I1 and I2, but actually just this piece and that piece. Okay, so there are two pieces. This is a simple example, right? If you have, for example, if you have sinusoidal function, wow, you will have a lot of pieces, right? Infinitely many pieces. Another example, say here, maybe I write here. If I draw a picture, okay, so, okay. Suppose g of x is sine 2 pi x. Okay? Sine 2 pi x. And so you have, okay, you have okay, now you have to divide the real line into infinitely many pieces. Why? Well, so you can divide them. Okay. Okay, and now in this open interval, the function, the sine function is monotone increasing and differentiable. But in this interval, so this is from, this is minus 1/2, and this is 1/2, and this is 3/2, and this is 5/2 minus 3/2 minus 5/2 here. Okay, so you see that. Okay, so you have infinitely many pieces. So you should divide the whole real line into infinitely many pieces, and each piece has length equal to 1. Okay, and in this piece, the sine function is monotone increasing, and in this piece is monotone decreasing, monotone increasing, monotone decreasing, right? See that? Okay, so this is a very common function you may encounter. All right, so okay, and for a particular y, say here, y here. All right, and you can see that every piece should be included. Okay, right? So the sum here should be infinite many. It's an infinite sum. Okay, because that you have so this piece here, right? Okay. So the point here. So suppose that we have x I1, x I2, maybe x I3, or maybe I use index by integer, and this is xi minus 1, xi minus 2, etc. Okay. So the j will range from minus infinity up to infinity. So the j will index for all possible integers. Okay. So now it's possible this sum is a serious sum. For this case, but this function is still well behaved, even though you have infinitely many pieces, but it's still well behaved. Okay. Because for ours, we say that it's well behaved if the image is open interval. You can see that for each piece, the range is from -1 to +1 without the endpoint, right? So every piece has the same range, and so their intersection would be the open interval from -1 to +1 for this particular example. So this is well behaved. And this one, of course, is well behaved. Why? Because we have only 2 pieces only. All right. So if the function can be divided into finitely many pieces, then this function will be well behaved. So only when you have infinite many pieces, you have to check whether this data processing function g of x is well behaved or not. Okay, but in practice, I mean, in your application, we believe that that the data processing function is well behaved. Okay. Well, if you are very, very lucky, you encounter one which is not well behaved, then you're really lucky because the chance is very small, and then you will need other tool to deal with that particular problem. Okay. Well, and I think this theorem will be broad enough for applications. Okay. So any questions? Any questions? Yeah, please. Yeah. So you see, so for this piece, this is from 1/2 to 3/2 for this, and for this piece is from 3/2 to 5/2, etc. Yeah. Okay. So that this is the boundary point, okay, we use this point to divide the whole real line into pieces. Okay, into pieces. And each piece should be an open interval. Okay, open interval. Any questions? All right. Okay, so, well, we have this situation. And of course, it is possible that the sum is empty sum. Why? For example, if the y is here, is here, y is here. Okay? So y is out of the range of the sine function. Okay? And then there is no corresponding x, right? Because it's out of range. So the sum is an empty set. And so in that case, the density function at this y is 0, of course. Okay? So if this is an empty sum, the value is 0. Okay? By our understanding. Okay? By our understanding. Any questions? Further questions? Okay. Now since the intersection of J, Aij plus 1, okay, is an open set. Okay? Because y contains here, y contains in the range of each piece, right? Y is contained in the range of each piece. So y should be in the intersection of the range of those pieces. Okay? And because g of x is well behaved, maybe I will say since g is well behaved. Okay, so the intersection of g of aij up to ai sub j plus 1 is non-empty open set. Okay, it's a non-empty open set. And select, so we select an open interval I such that y is in the I and contained in g of ai sub j up to ai sub j plus 1. Okay. So maybe I write here such that the y is in the open interval, and the open interval will be in g of ai sub j plus 1 for all j. Okay? All right, so these two examples is very simple because that the range of this branch is the same as the range of this piece, right? Just like this one. So this is very, maybe I raise the third one. maybe I read a third one. Okay, so this is g of x, y, g of x, okay. G of x here. Okay, and this is y here. And so we can, first of all, we can decompose. Okay. Right. So we have okay. Right. 1, 2, 3, 4, 5. We have 5 pieces. Okay. And the range of the first piece. So you can see here, this is minus infinity to, maybe you will say this is A1, A2, A3, A4, up to A1, and here's A1 up to A2. This is A2 up to A3. Here is A3 up to A4, and A4 up to infinity. So we have 4 pieces. And the range for the first piece would be here. Okay, so this is G of minus infinity A1. Okay, this is 1. And for the second piece, we have from here up to there. Okay, so this is second piece, G of A1, A2. Okay. Now for the so this one, the second piece up to here, and the third piece here. So we have from here up to there. Okay. So this is G of A2, A3. Okay. And this one. Okay. So this is from this one up to here. Okay. So G of A3, A4. Okay. And the last one, the red color. So this is from that one up to infinity. This is G of A4, infinity. Okay, and so you see that for y, all right, the index. So how many is here? Well, you have the green color, the yellow color, and the red color. So out of 5 pieces, all right, there are 3 pieces, all right. Their ranges contain y. Okay. So now, so in this particular situation, so that this is so I1 is equal to 1, 2. Okay, so I1 is 3, I2 is 4, I3 is 5. Okay, and so y is in the intersection of j from 1 to 3, and the g of a, ij plus 1. Okay. right? So it's the intersection of the three color. And because we have three open set, right? And their intersection must be open set too. And so we can we can select an interval I, and this interval we may select say here, say this interval, okay? So that is I. Okay, so I will contain in the intersection okay. So that is the situation. Okay, so this is maybe more interesting than the previous two examples there. Okay, now, as we know, in each piece, the G function is monotone, either monotone increasing or monotone decreasing, and differentiable. So it must have inverse function, okay? Right, and so as we know, HI is the inverse function of G of X in the ith piece. So for the first piece here, it's inverse. It's inverse. So H1. So you may say H1. It's a function from G of go back to right. Go back to here, and the H2 is from go back to H2, right? H3 is G, go back to, and H4, go back to, and H5, okay, so you have 5 inverse functions, but their domain are different. Okay, their domain are different. Yes, please. Because I define this is the first piece, so I use this A1, right? Well, yeah, I think this is because of the numbering. I'm sorry. Yeah, probably. Well, if you want reindexing, then that's fine. Well, you can use A2, and you define an A1 is minus infinity. Okay, that's 4, and you define A6 is the endpoint. Okay, in this case, then that's fine. Okay, so you will have. If you like, so 2 to infinity, okay. But I have to change everything, so that would be A2, and this would be 2. Four. 4 and 5. and infinity. Okay, and so I1 would be 3, right? 3, 4, 5. Okay, as you wish. Okay. Mm-hmm. Yeah, because the I index is used to represent the pieces. So I is the index used for pieces. All right. So for example, here we have 2 pieces. So I can be I from 1 to 2, and here I will be from minus infinity to up to infinity for all integers. Right. But for a particular y, y may not be in the range of certain piece, right? These two are special examples because for the y here I choose, the y will be in the range of every piece, just like that. But in here, this y, right, can only be in 3 out of the 5 pieces. Mm-hmm. And so I use I sub j. So j is the index for the pieces. Yeah, for I sub, because I already is the, you can say I is the first label, and j is the second label index as you do the programming in C, C++, or in Python. Okay, so I use a 2 label system. Yeah, hope to clarify the idea. Yeah, but if you got confused, I'm truly sorry about that. So, yeah. Yes, please. Oh, J is the index for okay. So for those pieces such that Y is inside the range of that piece. Yeah. Oh, sorry. Thank you so much. +1, yeah. Okay. My typo errors. Yes, thank you. Yeah. So it's I sub j and I sub j +1 because basically when I represent the piece, I use I, right? So I sub j is certain I, all right, and the next one would be I sub j +1, okay. So the 1 is in the first label, in the label of the index I. Now because I j +1 is different from I +1. This one is in the second label, okay, and that one would be in the first label. Okay, is that okay? Okay, any other questions? Very good. We have a nice discussion here. I like it. Okay, so all right. So these are examples. So we just choose an interval, all right, inside this intersection. Okay. Okay. Great. Now, so all right, and so we let j I sub j to be the image of I. Okay, so that must contain in A I sub j plus up to A I sub j +1. Okay. because now I is in the y-axis, right? Not in the x-axis, it's in the y-axis. All right, so that because I is a subset of each of the range of the pieces, and so under the inverse mapping H sub I sub j, okay, we have another interval j. All right, because I is an interval, then so j is also an interval, of course. Okay, and so where hi sub jy is the inverse function of g of x on ai sub j up to ai sub j plus 1. Okay. Okay, so we go back to here. The range, so that for the third one, for the green one, and so this goes, so we will go to here. Okay, and then up. Okay, so this one, so this is j. All right, so this is ji1, and this is ji2. This is ji3. So this I, okay, will have a range under H3, Hi1, and the range will be Ji1, Ji2, and Ji3. I1 is 3, I2 is 4, I3 is 5. Is that okay? Right? So we map there. All right, and so then, so once we figure out all this relationship here, now the P y in the interval. Okay? Okay, so the probability of this event is equal to the probability that the union of J and X is in Jij. And it's a disjoint union. Okay? Why? Why is a disjoint union? Well, the pieces, all the pieces on the x-axis, they are disjoint to each other. Right? So that Ji1 will be disjoint from Ji2, disjoint from Ji3. So they are disjoint. Okay, and so the event, these events are disjoint events. Questions? Okay, so this is if a non-limit condition, right? The random variable y is in the range is the same as that the random original data x is in j sub I sub j. And because this is a disjoint union, so we have the sum by finite additivity of the probability measure. Okay. The summation here. Okay, and what is that? Because x has PDF, right? So this is j I sub j, f of x, and d of x here. Okay? Now, Now, for the J's interval, okay? So for the J's interval, we let x equal to h sub I j y. All right? Okay? So we do basically change a variable. Right? And then, so all right, so this is it. And then d of x is equal to h prime I sub j of y and dy. Okay. Remember, because in each piece, the g function is monotone function. So the inverse function is also monotone function and differentiable. Okay? The g in each piece. Right? So, for example, in this piece, it's a monotone decreasing. Okay? It's monotone decreasing and differentiable. So the inverse function, all right, the inverse function is also monotone, all right, and differentiable. Okay, monotone differentiable, and it's monotone increasing. So the inverse. Anyway, so now, so we have this differentiable. So by change of variable, and so the integral jij fx becomes to go back to I, and the h of x h I j y, and the h I j prime y. But we have to take the f's value dy. The reason is that we always integrate over when over interval. We always from the smaller one to the bigger one, right? So from the smaller endpoint to the bigger endpoint. So that's why we have to take the f's value. Okay? Do you have any questions? I think this has been explained in calculus. Okay, so let's take an example, right? Suppose that the function is monotone increasing. Say here, let's say ai plus 1. Okay, so this is monotone increasing, right? All right, so g prime of x, you know, and the integration. Okay, so if we do, okay, so so maybe this is from, I suppose, and this is bi plus 1, say here. Okay, this is the range. So g is from ai plus 1 to bi plus 1. Okay, and so the integral, if you have, say, g of x and dy, and maybe I would say, okay, g. Maybe I have the integrand, and the y is from bi to bi. Suppose you have the integral, right, in the range of y from bi to bi plus 1. Okay, and you let y to be g of x. Okay, and g is monotone increasing and differentiable. All right, so dy becomes to g prime x and dx, and the g prime x is now with where g prime x would be greater than or equal to 0. Since if g monotone increasing. All right, so it's monotone increasing, and this one, and so that if we do the change of variables, bi is from ai, right? So bi is mapped by ai, and b sub I plus 1 is mapped by a sub I plus 1, and this is f and the g of x, and this is g prime of x and dx. That's fine. Now another case. Suppose you have, right? And so ai plus 1. Okay. And you have b I and bi plus 1. Because usually we wrote this way. Now, so this is, so y is g of x, and this is monotone decreasing. I have to, sorry, I have to put strictly. Monotone increasing and differentiable. Sorry. And this is strictly monotone decreasing and differentiable. Okay. Okay, so this is g of x. This is also y is g of x. All right, and so you are, so we will, in general, we will have bi, because the range is from bi to bi plus 1, and the f of y and dy. Okay? All right, so we have the same integral here, right? Because when we describe integral, the definite integral, the endpoint would be from smaller one to the bigger one, right? This is the convention. Okay? This is convention. All right, but when we do the change of variable here, all right, and so, and so dy becomes g prime of x and dx, right? Now, and where g prime of x would be less than or equal to 0, right? But I'm sorry, cannot equal to 0. Why? Because it's strict monotone. So it would be greater than 0. I'm sorry. I have to correct it. Because we put the strictly, I already corrected, so I must correct it here. Okay, again, here. If it's strictly monotone decreasing, then the derivative must be negative. Cannot be 0. Okay? All right, and so now we have g of x here, right? And the g prime of x and dx. The question is, bi, who map to bi? Who map to bi? It's ai plus 1. And who map to bi plus 1? Well, that is ai. Okay? And so when you turn to our conventional definite integral, okay, then we have to change the sign, right? Minus g prime by x and dx. And now this becomes positive. All right, so this is ai. And the absolute value dx. Okay, and this is, of course, all right. So that's why we put absolute value. I believe you learned this in calculus. Now you recall yourself already, right? Okay. That's fine. As a review, okay? As a review. Further questions? Okay, so that's why, because when I put I here, because conventionally we were integrate from the smaller endpoint to the bigger endpoint, right? And that's why we should put the absolute value here. Okay, so any questions about this one? So this is just purely change of variable. Okay. And by the change of variable. Okay. We have this one. All right. So for the J's interval here. Okay. All right, so now we combine them together. The probability that y is in this interval I is the summation of j. And now we have the same integration interval I here, but after the change of variable. Okay. All right, and now because the integrand always non-negative, this is non-negative, right? Because it's PDF. And the absolute value sign here, so it's negative. So the integrand is non-negative. So once the integrand is non-negative, then the sum and the integration can exchange the order. That is the general rule. Okay? I use this fact several times. Because the sum can be a series sum. If it's a finite sum, of course, no problem, because integration has linearity, right? But if the sum is a series sum, then you have to consider the validity to exchange the order of the serial sum and the integration, because these two are two limiting process. And in general, if the integrand can be positive, negative, then this may not be true. But if the integrand is non-negative, then you always be able to exchange them. Okay, and here. Right, maybe I have. Great. Okay. All right. So now we have the candidate, because by our, so if we have a PDF, then this probability should be able to express in this way. And consider here, so we will be happy to announce that if we assign F1, the PDF, to be the sum of then that would be very good, right? In this situation. So this one, so where is a PDF of Y? And Y is absolutely continuous. The end of proof. Okay. Well, the proof shouldn't take such a long time, but I like our discussion, right? And very pleased. I'm pleased to answer your question, if any. Okay. So I hope you really understand the proof. And after at the end of the proof, I believe you already know the exact meaning of the statement, right? Already. Every symbol, right? Every notation. Is that correct? Yeah, all right. So, okay, so we can go back to our application. All right, now we use this theorem to apply to the example. So revisit to our previous example with g of x is x squared. Okay, so now the first case, y is greater than 0 here. When y is greater than 0, so we look at here, we have two pieces, right? We have two pieces here. So when y is greater than 0, now we have two pieces. And so that we know G is from minus infinity to 0 goes to 0 to infinity. And the G 0 to infinity goes to 0 to infinity. All right, and the inverse H1 is from 0 to goes to so 0 to infinity goes to 0 to so minus, and so with and the H1 y is the minus square root of y. Okay, so the inverse of the first piece, all right, of G is minus y, right? And the H2 is from 0 to infinity goes to 0 to infinity, and the H2y is square root of y. All right? Okay, and so what is H1? So H1 prime of y is equal to minus dy, okay? And the H2 prime y is 1 over square root of y and the dy. And 2, and 2, okay? Yeah. All right. So F Fy little y, because we have two pieces, right? And so that okay, so we have f of x, and first piece h1 y, h1 prime y, okay, plus fx h2 y times h2 prime y absolute value, and the absolute value of this one, they have the same, so this will be 2 square root of y, and the f of x, the first one is minus square root of y, the second one is square root of y. Okay, and that would be the same as before, right? For y greater than 0. Okay. And for y less than 0, well, for y less than 0, then y that's not in the range of g, so that f of is 0. Okay. Basically, we can't find any piece in the sum, so the sum is empty. This is 0. Okay. So anyway, it's the same because this is not in the range. So the sum is an empty sum. Okay. Okay. Right. So this is the and all right. So let's take a short break for 5 minutes. Okay. Hey. Okay, so chapter 6 will deal with several random variables simultaneously, because in chapter 4 and chapter 5 we basically deal with a single random variable. Of course, sometimes we deal with more than one random variable. For example, when we consider the concept of expectation of an arbitrary random variables, indeed, we deal with the non-negative random variable first, and we use a sequence of simple random variable to approach it. And a sequence of simple random variable, they are different simple random variables. So indeed, we already consider infinitely many random variable already, right, in that situation. But the basic idea in chapter 4 and chapter 5 of focusing on a single random variable. But from this chapter, we will see to handle several random variables together. All right. But we start with, of course, we always start with a simple case like to have two random variables to consider. All right, so the first section is about joint distribution function. All right, so suppose we have two random variables. Okay, suppose we consider the simple case. Now, the joint cumulative distribution function so we can say JCDF notation is f of xy. So it's a function with two arguments. All right, it's defined as here is the joint probabilities of two events. Okay. So that is this event described by random variable x intersect another event described by random variable y. Okay, so a common means end, all right? So it means intersection. Okay, so joint cumulative distribution function is well defined, okay, because that this is an event of interest. This is also event of interest because x and y are random variables. And the intersection of two events of interest is also an event of interest. And then we can assign probability to it. Okay. So when you take arbitrary two random variables, you can always form their joint CDF. Okay. Now, so with the joint CDF f of xy of two random variables x and y, we can compute, okay, the CDF of x and y respectively. All right, as follows. Okay, so we can do that in the following way. Okay, now, first of all, we want to find the CDF of x. By definition, this is the probability of this event. Okay? And so we can express all right? And this event intersect with the total event, because y less than infinity is the total event, right? Because every random variable we consider it has real value. So real value must be any real number less than infinity. Okay? Right? So this is the first one. Now, right, so, and, right, so this is the first observation. And x, right, now, for each integer, for each positive integer n, all right, this event, this joint event will go up to as n goes to infinity, right? So we have a monotone increasing event. And the limit of this monotone increasing event is equal to this event. Right? Second observation. Is that okay? Okay, so now by using the continuity of probability function, so that would be the probability of x. Okay? And so this is the probability of the limit as n goes to infinity of. Okay? So this is the limit. By the continuity of P. Okay. By the continuity of P here. And so by our definition, this is just the joint CDF. It's n here. Okay. And so this is x, and we will say infinity. Okay. So this value will be defined to be here. So we can find out the CDF of the random variable x in this way. Any questions? All right, so similarly, all right, we can find the CDF of y. So again, this is probability that x okay. So okay, probability of the limit okay, and the limit and this is f of infinity y. Okay, and now f of x and f of sub y little y are called the marginal CDFs of x and y. Okay, so from joint CDF of two random variables x and y, we can evaluate or compute the marginal CDFs of x and y. These two marginal CDFs. Very quick, right? Just taking the limit like this one. Okay, now for further discussions, okay, so as we know, this is a random experiment. And it generates an outcome. All right, and the outcome may go through a measurement device X measurement device Y. So the output would be X omega. Okay. And then these two will be plotted in the plane. Okay, and so we can record these two measurement results simultaneously. Okay, and so we have a point here. Okay, So in many situations, we would like to see these two measurements simultaneously, and so represent these two measurements as a vector in the two-dimensional Euclidean space. Okay, so it's become the point here. So this go to here. So this would be our observation space, which is a plane. Okay, because we observe the result of two measurements devices simultaneously. Okay, so now we frequently ask for events by the joint measurement result. Okay, and for a single measurement means a single random variable x. We want the value will be in a certain interval, right, to be an event of interest. And similarly, we want that the result, so this is the point of observations in some interesting subset of the plane. Okay, so what kind of interesting subset of plane, like a interval on the real line, right? In 2 dimension, we were interested in so-called two cells. Okay, so a two cell, okay, a two cell in the real plane R2 is the Cartesian product I Cartesian product cross J of two intervals I and J on the real line. Okay, so for example, here is I interval, and here is J interval. So this area would be the two cell. Okay. And if here we have a cup crossed end, then this boundary will be included here. Okay. On the other hand, if we decide to include the boundary, the endpoint here, then we have include the boundary here. But this is still open, right? Because we have two open ends here. It depends, right? Interval can be open interval, closed interval, half open, half closed. Right? 4 kinds of intervals, as we considered before. Okay, and there are more varieties for two cells. Right? There are more varieties for two cells. Okay. Anyway. So, all right, so the Cartesian product would consist of all ordered pair, x, y, and x is in interval I and y is in interval j. Okay. So I hope you know Cartesian product before. And this is the reason why the plane is called a Cartesian plane. Okay, and this is Cartesian coordinate. Because Descartes, a French mathematician, invent such a notation. Okay, that is very important in the history. So now the event x, y, okay? Now the event is actually this event. Okay? So when we write the joint event like this one, it's same as to write that the pair, now we have a random vector because that we put two random variables together. So this is a random vector, two-dimensional random vector. This random vector is in the two cell, okay? In the two cell. So this is the same, okay? All right, so that this event is an event of interest, i.e. in the sigma algebra. Why? Because this is an event, because x is a random variable, so this is an event. And also this is an event. The intersection of two events of interest are also an event of interest, right? Okay. All right, so this event is an event of interest there. All right, and since we know this event Cartesian product with, okay, is equal to okay, and this is equal to so you can see there are quite a few different notation, but refer to the same event. Okay. So we know the joint CDF is actually the probability that the random vector is in these two cells. Okay, so it's in these two cells, and what is that would be, so if this is xy, this region, so this region is Cartesian product with, okay. So the joint CDF is the probability that the random vector is in this region. Okay. The probability that the random vector, or the probability that the measurement pair are located in this region, in these two cells. Okay, now, so this is the general case, right? Now, when x and y are both discrete, and take on one of the values AI and Bj respectively, we define joint probability mass function, the JPMF of x and y as little p xy AB. AI Bj equal to probability that x equal to AI, y such that Bj for all ij. And we define Pxy little p little y to be 0 for all xy not in either case Bj. Okay. Right? So if they are both discrete, then the joint PMF will be not all zeros, because that for some particular pairs AI and Bj, this probability, all right, may not be 0. Of course, joint PMF can be defined for two arbitrary random variables x and y as little p xy, the probability that x equal to little x, okay, for all. Okay, of course, just like a joint CDF, you can define joint PMF for two arbitrary random variables. Okay, but if x and y, both x and y, or any one of the two random variable is continuous, then the joint PMF will be all 0. Right? And in that case, there is no information at all to consider joint PMF. Right? So if any of x, either x or y, if either x or y is continuous, then joint PMF will be all 0. Okay? Will be all 0. No information. So such a function is not of any interest. Okay, so joint PMF will be interested whenever both x and y are discrete. Okay? Because they contain information. Okay. Any questions? Great. Now, the marginal PMFs of p x and little p of y of two discrete random variables x and y can be computed as follows. First of all, little px ai, because ai is one of possible values of random variable capital X. So this is p either ai. And this is probability of x little ai. Okay, intersect, or you can use intersect is the same as comma, and the union j y equal to bj. So this is total event. Why? Because for discrete random variable y, this event are atomic events, and the collection of all atomic events defined by random variable y is a partition of the total event S, right? So this is the together is the sum of space. We know that, right? So this is becomes to the probability that j x equal to ai, y equal to bj. Maybe you like intersection, okay? That's fine. Okay, and so by the countable additivity of probability measure, so you have, okay, so you sum over all possible j, and this is little p x y ai and the bj. Okay, so you sum over all possible j here. And similarly, bj is probability that y is bj here, and probability that disjoint union of I x equal to ai intersect with, okay, this is equal to the sum of space. And this is become to the joint union of ai bj. And this is summation of I, probability of x equal to ai, y equal to bj. So this is a summation of all I, little p, x, y, ai, bj. So marginal PMF can be obtained by sum over the joint PMF of x and y. Okay. Okay, so that is an interesting case. Now, okay, another interesting case is that we say two random variables, x and y, are called jointly, absolutely continuous. Okay, if there exists, all right, a non-negative, okay, and the integrable function f of xy on the real plane R2 such that for any two cell I call J on R square, okay, the probability that the joint measurement means the random vector is in these two cells can be obtained by double integration of this non-negative function f of xy. Okay. So if we can find a non-negative and the integrable function on R2, okay, such that this is true, all right, then we say these two random variables are jointly absolutely continuous. Okay, and in this case, okay, f of xy is called a joint probability density function so abbreviation is JPDF of random variables x and y. Okay, so if two random variables has a joint PDF, then they may have infinitely many joint PDF. Okay. Okay. In particular, right, the joint CDF of x and y can be computed as, okay, so as we know, the all right, so this is the probability of x is x. Okay, by definition, right? And as we know, this means that the random vector is in the two cell. Okay, it's in this two cell. So that would be from x. Oh, u v. Okay, so it becomes to this integral, this double integral here. Okay, so from the definition, right? Because that if we have a PDF, then it must have this identity here. And joint CDF is just a, yes, please. Oh, well, that's fine. Because that that is okay, you know, for some reason that we have dx dy because that it represents, if you regard it as a surface integral, then you will write dx dy because the tiny area is dx times dy. Okay, but if you because the surface integral can be decoupled because that the surface the region of in R2 is two cell, so it's a Cartesian product, so it can be represented as a repeated integral. If we represent it as a repeated integral, then in this way we should write because we integrate over y first because over j, and then over x. All right. So if I write this way, it means that we can evaluate the surface integral as the repeated double integral. And if I write it this way, I just say it's just a surface integral only. Okay. All right. So both of them are okay because they are the same because the integrand is non-negative. If the integrand is not non-negative, then in some case that you may not. But there's still some theorem that if it converts absolutely, means that if the integrand may be positive, negative, but if you put the absolute value, when you put the absolute value and the integral is still finite, then surface integral can be evaluated by repeated the double integral, and you can integrate first by y and then y, or you can exchange the order. That is a famous Fubini theorem. Okay, that is so. Yeah, good question. Yeah, so I just say in this case because the integrand is always non-negative, so it doesn't matter. Okay. Just like here, in here I deliberately say that I integrate over the second argument first. Okay. But that's a good question, good observation. Other questions? Okay, so you have, all right. So anyway, this is the same as if you like. Okay, the same. Okay, so this is saying that, okay, it should be, if repeated, you should write in this way. Okay. Okay, and it's better to, so I think it's better to write dx dy together. Okay, yeah, and it's better to write. There is no ambiguity. So you integrate over this region. Okay, you integrate over this region. Okay, and you have dx dy. This is dA, so the area, differential area. Okay. Okay, and so now, if x and y are jointly absolute continuous, the next question is, are x and y are absolutely continuous by themselves? Okay, and if the answer is yes, how do we compute the PDF of x and the PDF of y? Okay. All right, so assume that two random variables x and y are jointly absolutely continuous with a joint PDF f of x, y. Then okay, for any interval I, all right, we have, so now we check, right? We check the probability of this event. And this is probability of x in I and y is in R. Okay? And so this is I here and fxy and dy and dx. All right, so we know this probability actually can be computed in this way. You first evaluate the integral over y by fixed x first. And then after that, this is a function of x, and you integrate over the interval I. Okay, so observe that, right? We see that. And so that we can define a function which is this integral. Okay? So that, right? So this is a PDF of x. And then x is absolutely continuous. Right? So now immediately, okay, by checking, because this probability can be expressed in this way. So we can define the inner integral, improper integral, to be a function of x. And of course it's non-negative, right? It's non-negative because the integral is non-negative. So the integral is non-negative. And so x is absolutely continuous. And similarly, from to, so don't need to do this. So similarly, y is absolutely continuous with a PDF f of y to be the integral f of xy over x for all y in R. Okay. Okay, so our conclusion is that if x and y are jointly absolutely continuous with a joint PDF fxy, then x is absolutely continuous and y is also absolutely continuous. And then their respective PDF can be computed by the joint PDF, right? For integrate, to find the PDF over x, you integrate over y. To find the PDF for y, you integrate over x. Okay, so you have a nice property, right? You have nice property. But the converse may not be true. The converse may not be true. If we have two absolutely continuous random variable x and y, if x is absolutely continuous, y is also absolutely continuous, then x and y may not be jointly absolute continuous. May not. Okay. But one important case would be true. We will talk about that in the third section. All right, so I think I have to stop here. And again, the coming Saturday, we will have an early makeup lecture, okay? 2 days later. Okay, and please come here. If you cannot come here, so you can